And next up is Chuck. If you are on the same line as Janet, Chuck, you should be able to speak now.
Am I allowed to speak?
Yes, I can hear you.
Thank you, Miss Nikki.
You're welcome.
So PRSEF, and it's not PRSEF, it's PRSEF, is a regional science competition for grades 6 to 12, and we cover the western portion of Pennsylvania and Garrett County, Maryland. And Nikki mentioned this, but we have about 1,000 students each year in grades 6 to 12. Roughly 375 are high school students. And we are affiliated with the Science Society for Science and the Public, and they run the International Science and Engineering Fair. And students who attend ISEF are selected from affiliated fairs such as PRSEF. And so normally we send 4 students from PRSEF to ISEF every year. We could send more. We don't really have enough money for more, but in the right circumstances, we could find a way. So next slide. Hello, next slide. There we go. So ISEF is the world's largest and most prestigious science competition for high school students. Last year, they had 1,845 students from 75 countries, regions, and territories. That was a record. And of course, they had 4 for PRSEF from Pittsburgh here, from the Pittsburgh region. And students who get selected to attend ISEF get a free trip, among other things. But to go to ISEF, you get a free trip. And in 2020, that trip will take you to Anaheim, California, and you will be right across the street from Disneyland. Yeah, this is the sad part about it being muted. I can't get those reactions from folks. So let's go to the next slide, please. Oh, okay. So attending ISEF is the highlight of high school for most of the students, and we call them finalists. So, you get the opportunity to compete for cash and for prizes and for scholarships, and you're competing with the best and brightest students in the world. And one of our favorite stories here is about a young man named Ryan who competed at PRSEF here, and he got a half of a scholarship to go to WVU. And lo and behold, he wanted to go to WVU. He went to ISEF. He won a 4th award, but also people from West Virginia saw him there and said, "We want you to come to our school, and And he said, "Well, I already have half a scholarship." Well, they gave him the other half, so he got 4 years completely free to West Virginia University. And the top prize there is $75,000, but even a 4th award is worth $750. And so, but ISEF is just more than a competition. It's an opportunity to meet students who are just like you from all around the world. There are symposia also, including with the Nobel laureates. There are social functions, cultural enrichment, and just plain fun. And so next slide. Yeah, there we go. Thank you. Everyone who wants to go to ISEF completes a PRSEF application. So if you're in PRSEF, you have to complete an application. In order to be selected to attend ISEF, you need to fill out an additional application. It's just pretty simple. And you must also write a research paper. So the research that you've already done maybe already even exists in a paper or will be written as a paper, but you must write a proper research paper which must be submitted. And the paper is in the form of a publishable paper. And ideally, it should be publishable quality research. But every paper then is submitted and it's read, and then those that are deemed ISEF worthy from the first reading are sent to specialists who also read them and do additional evaluation. And finally, then, there are 10 or 15 papers are selected for further evaluation. And we have a team of judges who go around and talk to the students and look at their boards, and evaluate their work. And often the students may figure out that this isn't their regular judge, or may not, because there's not a badge on them saying, I'm judging ISEF. We don't, nobody gets any special or different treatment. And in fact, if the student asks, we'll answer accurately, but we won't tell you. I will go look at some projects myself. And finally, four of all the people submitted are selected to go to ISEF. We had about 72 papers submitted last year, 72 people plus teams who wanted to go to ISEF. We had, I think, a dozen who we reviewed on fair day, and we selected four very good students, by the way, who went. And here, I want to stop for a moment and say our students did okay at ISEF, and over the years have done okay. They've won some prizes, but we can always do better. And one of the things I would say a good reference for you to judge the quality of your project is to go out to look at abstracts from students who've won at ISEF. And there is a database online at Society for Science in the Public called abstracts.societyforscience.org. And there you'll be able to find every abstract for the last 5 or 6 years. Plus, you'll be able if you want to just look at the award winners in the category that you're interested in, you can go and look at those. And so you can see what people did that won awards. You can also see the top award, the $75,000 award there. So, the judging process for PRSEF and ISEF are similar. In fact, again, if a PRSEF or an ISEF, and this is whether you're talking about judging here in Pittsburgh for people to go, or people who are just being part of a PRSEF, or people who are at ISEF. The judges look at your board without you being present. They formulate questions. And then the second part of that, then you are then interviewed by that same judge. And so at ISEF, all students receive a 15-minute interview. But at PRSEF, this may run anywhere from 5 to 15 minutes, depending on the project and the judge and how many questions they have. And a group of judges will review all the projects. So you will have more than one judge look at your project, both at PRSEF and at ISEF. And then the judges caucus to form a consensus as to which projects get awards. And that's how it's done. I guess next slide here. Okay. I think I might have mentioned this, but for ISEF, then specifically, the judging process starts weeks ahead of time with your paper. So if what you've done kind of is not in your paper, you're not going to make it to the next review. And again, your paper should look like a research paper in a journal. And you should have consulted scholarly journals in formulating your research and getting background. So you should be familiar with what real research papers look like. And you really, really, really want to do proper references. And you could look in the student handbook to find how to do references, or look at the journals. Look at the papers that you looked at in order to do your background work. And we said wiki is not a reference, but you may use wiki to find a reference. And indeed, a URL is not a reference. In fact, URLs are really, even if you use the internet, not often required in a reference. So let's just assume the Journal of the American Medical Association, JAMA, is a print journal, but lots of people read it online. If you read JAMA and you read it online, you should use the reference for the print journal, because that reference will be there. You don't even need to say, oh, here's the URL, I read this online. It's completely irrelevant. But if you got a publication from the Environmental Protection Agency on let's say on a pesticide, and it's not a printed journal, then you would write the name, the author, the agency, the all complete reference, and then you would put the URL at the end, because it's only available online. And this is really crucial, because right now I am, but it's always been this way, the chair of the process reviews all the papers. So I read every paper, but for one of the first things I do is look carefully at the references. So this is kind of the first, this is your first impression, and it was like the references look pretty shady, and so that's you're already starting off on a bad foot. So then the judge will come and review your board first. They will look at the purpose and hypothesis, or the engineering goal and the conclusion. One of the first things a good judge will do is they say, do these things all make sense? Do they match? Is your experiment like a cohesive whole? So somebody someone gives a hypothesis, and then you look at their conclusion, and the conclusion doesn't have anything to do with the hypothesis. That's a red flag that there's something wrong with this project. And I guess now we're on to the next slide. There we go. Oh, okay. So that's the research paper structure. And we need the next slide. That's the next. We've already talked about. There we go. So what is it that judges look for? And the questions you need to ask yourself as you begin your research. So we want creative ideas, something unique. Research is about finding new knowledge, creating new knowledge. Now, that doesn't say that every project at PRSEF is original, because most of them aren't. But if the judges see 6 projects that are all basically the same, then none of them are likely to win an award anywhere. So you want to find something, though, that represents, and this is the thing for students, represents your unique interest. If you have a project that is similar to some existing project that you've seen, can you put your own twist on it? Can you try to be clever or interesting? And work is really critical. You need to do the right amount of work. More samples are always better. And how many is enough depends on a number of things. If you do an experiment that takes weeks to perform, you might only do 1 run of that experiment. Although typically you should do 2 runs of any process, so to show that they are the results, that your methods and the results are reproducible. But if you're running, a thing that takes a very, very long time, then you might only run it once. But if you did something that took a day to run, you might set it up 10 or 20 days and set it up and run and get that 10 or 20 sets of data from trials. Growing plants. Lots of people grow plants. That's a fine project. But a lower level student should probably grow, 20 or 30 plants. High school plant student doing a plant experiment needs to do 100 more plants. Now, if you're growing huge plants, maybe you might want to do fewer. But typically, little bean pots or bean plants, do more than you think you should. Doing tests with other students, simple tests should include at least 10. You can't do your 5 people in your family and expect to win anything. And the whole tenor of this part of this, this presentation is about what it takes to win, or what it takes to do a good project. Everybody who does a project and has fun doing it, that's good. They're winners. We have a bunch of those students, and we want those students to come and compete and have fun. But if they want to do better, they want to do something that's going to impress people, they need to, to listen to this kind of information. So more is better. Again, simple tests, and maybe 10 people. But if you're in sixth, seventh, or eighth grade, you probably want to do at least 30, and you might want to do 50 or 100 if you're in high school, or more. You know, I had a kid from the Pittsburgh Gifted program, a fifth grader, who had a survey, and he was doing it, and he went out went out and stood on the corner in Squirrel Hill and Lawrenceville and one other place, and he got results from 380 people. That was a good project. He got something that meant something. And if you're testing some physical factor, and I'll keep this simple because sometimes we have, like, especially in junior high and the sixth graders, they'll build cars and run them down a track. Okay, it's been done 100 times, but you know, there'll be 10 runs for each car. If and nobody's going to pay much attention to that. If you do 100 runs for each car, and those are pretty quick, that's one might actually get some attention. Someone might think you were serious. Now, if you're building something complicated, you can probably only build one. But if you're building something similar in an engineering context, then you can and probably should build and test several of them. And of course, no researcher should ever forget controls. So for some standard condition. So if you do your project then in a couple of hours, the judges any decent judge will see that, and you're not going to get a good score. Good research takes some commitment of time. And then we're going to finally, let's talk about analysis, because this is very important and it's often ignored by the students. Your numbers tell the story. So did your experiment give you the correct numbers to test your hypothesis? In other words, did that data that you found, did that actually match what you said you were looking for? And often, again, you should have many trials of the same phenomenon so that your numbers are more meaningful. So sixth, seventh, and eighth graders should be able to report means, average values, and at minimum. I mean, you can run these things on Excel and get all kinds of good statistical analysis. And it's pretty straightforward that just about anybody should be able to understand. High school students should be, absolutely, minimum should be using some basic statistical analysis, like a t-test or a p-test, to look at the difference in the analysis of variance. Again, program calculators, even programs like Excel, will do a lot of things. Have the students go to the math teacher as a resource for statistical analysis so that you understand what you're doing in Excel. And finally, students should be clear about what you did, what you as the experimenter did, and what was done for you in the lab. So, if you did some tests, and we've had kids who've done some really good scientific research, and they ran their samples through a GCMS, and they didn't. Some ran them themselves. Some of them learned and were able to. But you can't expect that every lab is going to let you use their expensive equipment. But if the lab ran those for you, that's fine. I also had kids who built the test stands, test jigs. And one was very nicely welded. And I had a eighth grader who I asked him, "Did someone build this for you? Because that's okay. If your dad built this for you, because you're not expected to know how to weld." "Oh no, my uncle's a welder. I had him teach me how to weld it, and I welded it." Again, not necessary, but impressive. So, next slide then. Okay, writing for your paper, for your board. Clear and simple. Clear and simple. Short and simple and to the point. And, when you're writing your conclusion, the first thing should be, I found that aspirin cures cancer. If that's what your data says, I found that aspirin cures cancer. And then you can qualify. I found that aspirin cures cancer when you take it for 20 years every day in 100 to 150 milligram dose. But you want to say what you did and then qualify it with the conditions. People shouldn't have to hunt for what you did. And you would be surprised. I get 2 paragraphs before somebody says, "Oh yeah, this is what I found." No, the first thing in your conclusion should be, what did you find? I built the greatest rocket ever built. That's a conclusion. Don't qualify first. Figures and tables should always, 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 always have titles and units. What are the units that you're measuring? And again, it should be, what did you do and what do you know? Let me just one more slide here. Boop. Talking to the judges. The judges are there. They're volunteering their time. They want to be there. So your student should be nervous. But good judges won't let you talk on and on. You should have a prepared talk that's around a minute plus or minus long. And it should start with, what did you find? What did you do? And then the judges will probably want to ask questions. If the judge doesn't ask questions, then have something more to say, like, oh, I chose this research topic because I have this general interest in the subject. This is what we did. Because you have to remember, the student is the expert in his or her own project, and they should have that confidence and talk up to the judge, and the judges will love you for it. And, I guess there's one last thing, and that's the last thing on the bottom of this slide. If you don't know the answer, say, I don't know. You can say maybe, oh, I don't know the answer, but I think it might be XYZ. That's that's okay, but you should admit that you don't know the answer to something. And, make sure you understand the underlying science. So if you're testing a pesticide, you should know what's in the pesticide, for example. If you were testing Roundup, what's in Roundup. Okay, so that's everything. And we're on to Tom.